morning everyone, Dr. Nat here. So I am going to continue doing this lecture by recording because it's history and I know you guys need to go over this many times to get it into your heads. So this is why I'm recording it. But after this lecture, I'm going to give you an assignment and that would have some marks to your overall grade. Okay? So I hope that everyone is okay with that. So we're going to continue. In the previous lecture, we were talking about the 3 generations of computer. The first one being computers that were based off vacuum tubes. We saw ENIAC, we saw ADVAC, right? And the problem with ENIAC was that it couldn't store programs. And then the ADVAC, which was based on John von Neumann, which was a mathematician guy, he came up with the IAS computer structure, and we talked about that as well. And then after the ADVAC, if I'm not mistaken, we were talking about how the transistors came about, which came the second generation of computers. And then after the second generation of computers, we have the third generation of computers based off integrated circuit, which is where we are now. And after that came many versions of computers, and we're going to continue talking about that today. So IBM brought out a family of products called System/360 or S/360. So what was different about this product that is brought out by IBM? Well, for instance, the computers that they brought out could be compatible with each other. They are compatible. What does that mean? What does compatibility mean in this sense? It means that if computer A can run a certain program, then computer B can also run the same program despite not having the same processing speed, despite not having the same memory, but they could still run the same programs. The only difference would be on how fast they could run or execute the program. IBM was no longer focusing on creating computers that were automating tasks, which was done before by the ADVAC, right? Now it wants to have this compatibility, meaning to say it wants a program that can be executed by all of its computers. So there's no more writing a specific program for this computer based on its requirement, but it should be compatible across its products. Very good idea. So this was like a bold move by IBM, honestly, because at that time, everyone already was comfortable with their computers, right? And if they were to introduce this system, everyone had to change their computers for the computers to be compatible with each other, right? So was it a success? Of course, because now IBM, after that, IBM became like the #1 major computer manufacturer. Hooray! And then, so what were the different models that were brought out by IBM? They had the Model 30, Model 40, Model 50, 65, and 75. So what were the differences between them? They had different memory sizes. They had different processing cycle time. The higher the number of the model, the faster it was. The higher the number of the model, the more memory that it has. So let me write this. So you're going across like that, okay? And then you would have more number of I/O ports should you have a higher number model. It was like, think of it like this. So I have 2 HP laptops, for example. I don't really have 2 HP laptops. So my first HP laptop has a processor of i5 Intel, right? And my other HP laptop has a processor of i7 Intel. But both of them can run the same software. Both of them can run any programs that I put into them because they are compatible. So this was what IBM envisioned and it carried out. So this concept was extremely novel and extremely successful. A customer with a modest requirement, meaning to say they have like a certain budget and they don't really want a fast computer, so they could go for the lower end model such as Model 30. Whereas for someone who uses the computer heavily to do like very intense calculations or simulations, they could go for the Model 75, and both would work with the same program. Only the difference was on how fast it could execute the program. It was excellent. So the characteristics of the family, let me read this for you. It has similar or identical instruction set, of course. It would have a similar or identical operating system. Across the model, it would have increasing speed. Across the model, it will have increasing number of I/O ports. Across the model, it would have increasing memory size. And across the model, of course, it would have increasing cost. So let me say that again. It would have increasing memory, it would have increasing cost, it would have the same, what would be the same? The similar traits would be the instruction set and also the operating system. Those two are the same. The rest would be increasing number of I/O ports, increasing number of memory, increasing cost, increasing speed. Okay, so those are things that you can, I think those are common sense. The two things that you need to remember that are similar across the family is the operating system and the instruction set. Okay, moving on. Before I tell you about PDP-8, I would like to inform you that the IBM family or the computer cost hundreds of thousands of dollars. So it wasn't really affordable, but commercial businesses could afford it. So now, in the same year, we have PDP-8 being introduced. What was it? It was a mini computer. It's not IBM. It's from a rival company called DEC, Digital Equipment Corporation. So you have all these models, PDP-8, PDP-8/5, and all of the stuff. And it would have different data rate. It would be different in volume, as you can see over here, in cubic feet. So the later models would be very small in volume size. And this was the innovation. First, it was automatic wire wrapping production, serial instruction, medium scale integrated, smaller cabinet, omnibus, half-size cabinet, and then lastly, it would have the semiconductor memory, floating point processor. The semiconductor is still very much relevant up to this day. So with this introduction of the PDP-8, the DEC company came in second as the global computer manufacturer. Its low cost and small size of the PDP-8 enabled other manufacturers to use this PDP and integrate it in their own systems. And you would know this as OEM. OEM, Original Equipment Manufacturer. What they did was they wanted to do their own systems, but they are not like the large-scale IBM and DEC. So if they wanted to come up with a product that has some type of intelligence to it, they would use this PDP-8, a form of a mini computer, put it into their system, and their system would be OEM, the Original Equipment Manufacturer. Okay? Next, moving on. So this is how the PDP-8 looks like. So they introduced the omnibus, as I showed to you in this table over here. We have the omnibus introduced in PDP-8/E. So the omnibus is, we still see buses as of now. So it was very, I would say it was very ahead of its time actually. So you would have the console, controller, CPU, main memory, I/O module, other I/O modules, depending on how many I/O modules that you need, and they were all connected by an omnibus. You can see that the structure is very different compared to the IAS computer structure that we've seen before, which used a main memory switch, right? So they have this bus. Very awesome. So after the third generation, we had LSI, large-scale integration. What does large-scale integration mean? It means that at least 1,000 components can be placed on a single integrated circuit chip. 1,000. Let me write that down. 1,000 Sorry, I'm using my trackpad to write, very hard. And then after the LSI, we have the VLSI, which could fit 10,000 components per chip. That's crazy. 10,000. What is 10,000 compared to the billions that we have now? I can't imagine how bright they were. And then we have the ULSI. I think my face is blocking this. ULSI is ultra large scale integration, whereby you would have 1 billion components on a single chip. Very mind-blowing. So with the rapid pace of technology, the high rate of introduction of new products, and the importance of software and communications as well as hardware, the classification of generation becomes less clear. So after the 3rd generation, we don't really call them as 4th generation, 5th generation, 6th generation. We don't have that. We only have the LSI, VLSI. ULSI is where we are at currently, with billions of chips, with billions of components on a single chip. So before we have our semiconductor memory that we are using right now, we are still using semiconductor. So before the semiconductor, we were using, most computer memory was constructed from tiny rings of ferromagnetic material, very small, about a 1/16 of an inch. So 1 inch, we divide that by 16, very small in diameter. So the rings were strung up on grids of fine wire, so you have a lot of that. They are very small, so you would have a lot of memory. And they were suspended on small screens inside the computer. And if it was magnetized in one way, you know that magnetism has direction, it's a vector. So if it was magnetized in one way, that would be the binary number 1. And if it was magnetized the other way, it would be binary number 0. So each ring was called a core. You've heard of core before, right? The name is very much relevant. I guess it sticks, even though we are no longer using the ferromagnetic rings. So, however, these rings were very bulky, they were very expensive, and used destructive readout. The simple act of reading a core erased data stored in it. So it was destructive. This is what destructive means. Every time it reads the data, it would erase the data that was already stored inside. So you would have to start fresh every time. Therefore, it was necessary to install circuits to restore the data as soon as it has been extracted. So the way that they overcame this was after it was being stored, they would extract it immediately, save it somewhere else, because every time it would run, it would erase the data that was inside. So came along the semiconductor memory. In 1970, the Fairchild produced the first relatively capacious semiconductor memory. The chip was about the size of a single core. Very small, could hold 256 bits of memory. It was non-destructive, meaning to say if it was storing data and it was running, it would not erase the data. And it was much faster than the core. So in 1974, the price of a semiconductor memory dropped down below the price per bit of a core memory, meaning to say that your semiconductor memory versus the ring is much more expensive. So people would obviously want to use the cheaper one, and it was much faster than the core. So there has been a continuing rapid decline in memory cost, accompanied by a corresponding increase in physical memory density. So people were demanding more memory. So naturally, they would go for the cheaper one because they could have more of that. And then the developments in memory and processor technologies changed the nature of computers in less than a decade. So the semicon was novel and very successful as well, just like the IBM family products. Not relevant, but they are both successful. So since 1970, semiconductor memory has been through more than 13 generations. Each generation has provided 4 times the storage density, accompanied by declining costs. So every time you hear Intel coming out with a new generation, you know that the storage density is 4 times better than the previous generation. So for example, you have your i5, generation 5, i5 generation 7. So these two, generation 5 and generation 7 times 4 times 4, you would get your generation 4 storage. It would be better, much better than the i5 or the i6. Sorry, the generation 6 and generation 5. Even though they are still called i5. Okay? So moving on, so that was memory. So if our memory was rapidly evolving, we also need to match it up with our processor, right? So just as the density of elements on the memory chips has continued to rise, we were fitting in more components on our single chip. The density of element on processor chips also needed to rise as well. So as time went on, more and more elements were placed on a single chip so that fewer chips were needed to construct a single computer processor. So you didn't need as much chips as before because one chip already had a lot of components or elements. So a breakthrough was achieved in 1971 by Intel. It developed the 4004. It was the first chip to contain all components of a CPU on a single chip. Could it do at that time? It was able to add two 4-bit numbers. Excuse my handwriting, very bad. So it could only do that. Very primitive, right? But at that time, that was the capability of our computers. And apart from the addition, it could only multiply by repeated addition. It was quite bad. So by today's standard, the 4004 is really bad. We won't use it anymore, ever. So this evolution, and after that, the Intel introduced a different microprocessor called the 8008 or 8008. So it was the first 8-bit microprocessor. And then after 2 years, Intel developed the 8080. It was still an 8-bit microprocessor. The difference was that the 4004 and 8008 was designed as a microprocessor for a specific application. It was not intended to be used as a general purpose CPU. But the 8080, which was faster, has a richer instruction set, and has a larger addressing capability, could be used for general purpose. You need to say it was up to your imagination on how you would want to use it, because it is supposed to be general purpose. Okay. So this is the evolution of Intel microprocessors. We started with the 4004, 8008, the 8-bit microprocessor, and then we had the 8080, which was our general purpose CPU, and then we have our 8086, 8088. You don't have to memorize this, you only have to know the progression. So the speed was obviously going to increase, the bus width was also increasing. Here they introduced the 8-bit, and then they retained the 8-bit over here. And here they introduced two types of microprocessor, one as 16 and the other as 8, but they would have approximately relatively similar clock speeds, right? The only difference was the bits. And then you would have increasing number of transistors. You would see here in thousands for the after generation, and the feature size was obviously going to be much smaller. And then the addressable memory, this was 1 megabyte, quite small, but that was what they were working with at the time. And then the 1980s also introduced more processors, and from 5 megahertz they were doing 50 megahertz. From 8 bits they were introducing 32 bits, and then from 29,000 we now have millions, and then the size was getting much smaller, up to 1 micrometer, and the addressable memory has now become gigabytes. Amazing. Now we have 64 bits as well. So this was in the 1990s. We have 64 bits, right? Previously it was 32, and then now we have 64 gigabytes, and then previously it was 50 megahertz. Now it was becoming 300. And then in the recent, this is not quite recent, this is in 2010, where i7 was introduced. We were still using 64. we were using 64. This was retained actually, and then the memory was still 64 terabytes. From the 1990s to the 2010, I wouldn't say there was much of a hike except for the clock speed. So your assignment is to find out the most recent processor, make a table on when it was introduced, the clock speeds, the bus width if it is relevant, number of transistors, the feature size, the addressable memory, the virtual core, the cache. Find out. I need at least 5 for between 2010 to 2022. Yep. Okay, so now we are going to talk about microprocessor speed. Previously, we were talking about memory. Before the semiconductor memory was introduced, we were using ferromagnetic rings. And then we were also talking about the microprocessors, how it evolved from the 1970s up to 2010. The clock speed, the bus width, the memory, right? And all those stuff. So now we are talking about the microprocessor speed. The raw speed of microprocessor will not achieve its full potential unless the microprocessor designer could figure out how to utilize its full potential. Now just imagine you want someone to work really fast. They can work really fast, but you're not giving them certain instructions to do. For example, I want you to do a homework that consists of first addition, second multiplication, third division, fourth would be multiplication again, and addition. So I know that I want you to achieve all these steps, but I'm not giving it to you. I want you to be very fast in solving a problem, but I'm not giving you the steps. So if I were to tell you, hey, to solve this problem at a really fast speed, you need to do these 5 steps. I'm giving it to you. I'm like hinting to you how to do it. So this is what the technique does to help the microprocessor achieve its full speed. They are giving the steps. So you have the pipelining, you have the branch prediction, you have the data flow analysis, you have the speculative execution. Without techniques, you can be fast, but at the same time you need to like, oh, what should I do next? What should I do next? So that hampers the speed, right? So if you were to introduce these techniques and teach it, these techniques, they could execute things at a much faster speed and be more efficient. Okay, so what does a pipelining do? The processor moves data or instructions into a conceptual pipe with all stages of the pipe processing simultaneously. Let's just be familiar with the terms first, and then we'll talk more on this. And then we have the branch prediction, whereby the processor looks ahead in the instruction code. Basically, it's trying to predict what it needs to do, fetch from the memory, and predicts which branches or groups are likely to be processed next. Then you have the data flow analysis, whereby the processor analyzes which instructions are dependent on each other's results to create an optimized schedule. And then you have your speculative execution, which uses branch prediction and data flow analysis to speculatively execute instructions ahead of their actual appearance. So a lot of prediction going on here. You have your branch prediction and your speculative execution, doing things ahead, predicting things ahead, whereby the data, how you organize the data or how you process the data is done by the pipelining and data flow analysis. So we know that the processor is like super speedy ahead of a lot of other components because all the efforts are focused into like creating better processes, right? So some components could not catch up to this. So what happens is that when you have these components within the same computer, they create a mismatch in terms of speed. So there is a need for performance balance. So what is a performance balance? It is an adjusting of the organization and architecture to compensate for the mismatch among the capabilities of various components. So So this is what performance balance means. So this is an example of how what are the architectural examples to do the performance balance. Okay, so this figure shows the typical I/O device data rates. So you can see here that you have the gigabit Ethernet, which uses a data rate of 10 to the power of 9. Then you have your graphics display, your hard disk, your Ethernet, your optical disk, your scanner, your laser printer, your floppy disk, your modem, mouse, and keyboard. So I've told you before that these things that are connected to your computer is called a peripheral device. They are attached to your computer remotely. They are attached to your computer locally. They are not remote, which means that they are not considered IoT. They are connected, right? Okay, so despite being connected locally, they can demand data rates like this. And this requires a movement of data between the computer to the I/O device, and you need it to move fast. The data between the computer and also the I/O device needs to be fast. If not, if you move your mouse, it's going to lag. You won't see your mouse moving smoothly. This is because sometimes your computer cannot support the throughput data that these devices request. So how do you overcome this type of problem? Is that you can employ multiprocessors. So here comes our multiprocessors. So again, you have different types of peripheral devices. They demand different data rates. Your computer needs to be equipped to handle the data movement. Okay? The use of multiple processors configurations can help with this. Let's talk about that. Okay, so improvements in chip organization and architecture. Let's talk about that as designers wrestle with the challenge of balancing processor performance with that of main memory and other computer components. The need to increase processor speed remains. Despite of all of the problems that we have seen, they still want something fast. Of course, we all want something. We all want our computers to be really, really fast, right? It would mean really good graphics. It would mean really, really good, smooth experience in using a digital tablet, a smooth experience in using a mouse, keyboards, and stuff like that. So to do the improvement in chip organization and architecture, you would have to increase the hardware speed of processor. You have to increase the size and speed of the cache. You would also have to change the processor organization and architecture. This is the job of a processor designer. You would introduce parallelism to handle the data, increase the effective speed of instruction execution, teach them how to execute effectively. Okay? And then you have problems with clock speed and login density, which is related to the power and RC delay and also memory latency. Memory latency means that the memory speeds lag processor speed. The memory cannot keep up with the fast speed of the processor, as previously we have discussed. And what about the RC delay? The speed at which electrons flow limited by resistance and capacitance of metal wires connecting them. This is basic circuit, RC. You've seen this in your YouTube. So sometimes your electronics are not as fast as your processor. Weird, right? But this is the reality of things. The delay increases as RC product increases. Wire interconnect thinner, increasing resistance. Wire closer together, increasing capacitance. So these are things that the circuit designer has to think about. And then for power, the power density increases with density of logic and clock speed. Something to think about as well. And power the higher the power that you use, the more heat that you need to dissipate. So how do you design something that dissipates heat effectively? These are all the problems that you need to be aware of when you want to design your processor. Your computer. So this is processor trends. We've talked about this before. And now I would like to talk about multi-core.